All right, welcome to Unit 16.3, Titrations. This is the second half of the first half of our acid and base unit. So recall, we're going to take two tests in this unit, and this is the second half of that first test. Again, the first half would have been the complete and net ionic equations, and the second half are these, which we call titrations. All right, so here is a titration setup. We'd have a burette, which is a very fancy piece of glassware that is usually hooked to a ring stand. It's very similar to how we'll have it in our lab. And it can very slowly and very accurately drip small amounts of either acid or base into, though they have it going into a flask, we'll probably have it going into a beaker, but the point is you can add very, very accurate, very small amounts of one compound into another. And that's the idea of a titration. We're going to add a known substance from the burette into an unknown substance to figure out what the unknown substance is. Commonly, titrations use an acid and a base, which is what we'll do, in a reaction called a neutralization reaction. And again, we'll have an unknown amount of acid, and we'll add base to titrate it to figure out how strong that acid is. All right, the substance we're analyzing, it'll be in the bottom here, will be called the analyte. And it'll be an unknown sample of acid. We don't know the strength of the acid. That's called our analyte. The material that we do know, so we'll have a base then of known strength, and that'll be in the burette. That's called the titrant. So make sure you're familiar with the terms. You're titrating the analyte, the unknown, with the known material called the titrant. And then again, this long piece of glassware that holds the titrant is called the burette. And again, the point of a burette is it allows you to measure very accurately very small samples of material. All right, so the idea with the titration is it allows you, again, to determine the strength of an acid, or you could do the strength of an unknown base, what the pH of the acid or the base is, and then you can figure out the concentration of that acid or base by adding a known substance. In order to figure out where your base and your acid are equal, we use an indicator, which will change colors. Now, as this image shows, you always have to make sure that you swirl. So kind of just pick up the glassware and just kind of swirl it around a little bit every time you add a little bit of your titrant. And the reason for this is you might get a slight color change. You might get this splash of pink just because that one little area is really, really concentrated, because that's exactly where the titrant was being added. But when you swirl it, you'll notice the pink goes away, at least for another drop or two. What you want to try to do is you want to try to get your solution, your indicator, to turn a very dull pink. And even when you swirl, it doesn't go away. If you get it to that very dull pink, you've managed to hit spot on the end point of the reaction. And that's where your base equals your acid. If you go a little bit too far, you continue to add base, which we will do. We will continue to add base. Your light pink will turn into a much darker pink. So if you skip straight from a clear color to that dark pink, you kind of went right over the end point. Hey, that happens from time to time. But do try to land it straight on the end point if possible. So a little bit about pH. We'll work more with that next chapter. But just a little bit about pH. It's a measure of the strength, or the how acidic or basic a solution is. So a neutral pH a neutral solution has a pH of 7. An acidic pH goes lower than 7, and a basic pH goes higher than 7. So when we run a titration, we end up with a curve that looks something like this. This is, we started with an acid, an unknown acid. We added base, and that's why our pH goes higher. What we're trying to find is what's called the equivalence point. And again, that should be the same as the end point. If you choose a poor indicator, you can miss your equivalence point with the end point. But since I'm choosing the indicator for you, we'll make sure we have a good indicator, and we should have the equivalence point and the end point should be the same. So again, that's where our acid equals our base. So again, on the graph on the left here, the analyte is an acid. What we're trying to analyze, what we're trying to figure out what it is, that's an acid. Notice how the pH starts low, that makes it acidic. As we add titrant, so the titrant is what we're adding to it, the pH goes up, so that tells us that we're adding base. The more base we add, the higher our pH climbs. Again, at the pH is equal to 7, that's our equivalence point, and that's where the amount of acid equals the amount of base. We've got a second graph here, and that's this time we would have an analyte of a base. We'd have an unknown base, and we would add acid. So the titrant on this case would be acid, and again, we're starting with a high pH, and it's dropping, it's going lower because we're adding acid. But once again, the equivalence point is where acid and base are equal, which in this case is at a pH of 7. All right, so how do we figure out then what our concentration of acid is? So we know the concentration of base, and we need to figure out the concentration of acid. So here's an example. A 20 milliliter sample of hydrochloric acid solution is titrated with 27.4 milliliters of a 0.0154 molar, again, that's our molarity, barium hydroxide. So barium hydroxide is our base, and we're trying to reach the equivalent point. So it took 27.4 milliliters to reach that equivalent point. And we need to figure out the concentration of our acid. It always starts with a balanced chemical equation. So make sure to write that first. HCl plus here's barium hydroxide. It's a double displacement. The barium is going to be our positively charged cation. He's going to reform with the negatively charged anion. That would be the chloride ion to form barium chloride. And then H will go with the hydroxide, and you'll get H2O, which is water. To balance it correctly, I need 2 H2Os and 2 HCl's. Don't forget about barium having that positive 2 charge. So again, here's the idea. We'd have our burette, and we have our barium hydroxide, our base, in the burette. In the bottom of our flask, or beaker, we're going to have our 20 milliliters of our hydrochloric acid. So here's our base. We're going to pour it into the acid. So you see us draining the base into the acid. It goes down 13.38 cubic centimeters, or 13.38 milliliters. And we're trying to hit that end point again where it changes colors. Again, for us, it happened here, 27.4 milliliters. We reached the end point. That should be at the pH of 7, should be right in the middle of our graph there, the equivalence point. All right, so mathematically, here's what we're going to do. Again, we're looking for a concentration, that's a molarity, moles per liter of hydrochloric acid. I'm going to tell you right now, it really, really helps to label at HCl, HCl. You're going to get confused. You're going to be working with a lot of different volumes this chapter. Label them, label them. All right, so since I have a volume of HCl on the bottom, I want to put my volume of HCl on the bottom. So I started with 20 milliliters of hydrochloric acid. That goes on the bottom. That was equal to 27.4 milliliters of barium hydroxide. So there's a starting conversion factor. My base on top of my acid, because I want the acid volume on bottom. Okay. Here's my concentration, moles per liter of base, barium hydroxide. So that's going to cancel out my milliliters of barium hydroxide and leave me with moles of barium hydroxide. Next, I can use my balanced chemical equation to convert from moles of barium hydroxide to moles of hydrochloric acid. It's a 2-to-1 ratio. Finally, I had to make a little more room here. Finally, then, I want to make sure that I convert my 20 milliliters into liters. I want moles over liters. So when all my units are done and canceled out, my milliliters of barium hydroxide cancel, my moles of barium hydroxide cancel, I'm left with moles of hydrochloric acid over liters of hydrochloric acid. That's a molarity of hydrochloric acid. And I have determined that the strength of my hydrochloric acid is 0.0422 molar. Let's take a look at another example. Calculate the molarity of acetic acid when 21.2 milliliters of acetic acid is titrated with 15.5 milliliters of a 0.215 molar potassium hydroxide solution. All right, so again, we're looking for the strength of our acetic acid. We have a volume of known base, 0.215 potassium hydroxide. So I'm going to titrate my acid with my base until I reach the endpoint. How do I know I reached the endpoint? Because the color changed. Look at that. I've got my color change. I've reached the endpoint. It took me 15.5 milliliters to get there. Excellent. And on a graph, here's what that looks like. The endpoint should be the equivalence point. So we're going to write our balanced chemical equation. Acetic acid plus potassium hydroxide gives us potassium acetate and water. Again, when I set up my concentration, moles per liter of acetic acid, I have my volume of acetic acid on the bottom.
Pardon the interruption.
So I want to make sure I put the volume of my acetic acid on the bottom. That's equal to
the awning for bus 271. Again, students who ride bus 126, please wait under the awning for bus 271. And last but not least, let's wish Mrs. Rose, our Spanish teacher, a wonderful happy birthday.
All right, it's Miss
Happy
Rose's birthday today.
Ms. Rose.
All right, sorry for the interruption. So again, here's my concentration of base now. So I went from milliliters of KOH to moles of KOH. And now with a balanced chemical equation, I can go from moles of KOH to moles of acetic acid. Finally then, don't forget, we're working with milliliters of acetic acid and we want liters. So make that final conversion. And I figure out the concentration of my acetic acid to be 0.157 molar. All right, one more example for you. Calculate the molarity of acetic acid when a 21.2 milliliters of acetic acid is titrated with 15.5 milliliters of 0.215 molar potassium hydroxide. We're going to go through the titration. We have the end point, which is hopefully equal to the equivalence point. We set up our equation. Again, we're looking for a concentration of acetic acid. We want to put our volume of acetic acid on the bottom. It's equal to 15.5 milliliters of KOH. Here's the strength of our KOH. That cancels out milliliters of KOH. We can then use our balanced chemical equation to go from moles of KOH to moles of acetic acid. And finally, don't forget, we have a milliliters of acetic acid, but we want a liters of acetic acid.
Are you getting a reminder on your computer for future ready skills on your calendar?
No, I didn't accept the invitation.
What is it?
Some meeting we have to go to. Kathy sent out a thing.
Where is it?
So another one. What volume of 6 molar sulfuric acid is required to neutralize 5.6 grams of sodium hydroxide? Well, this one's a little bit outside the box, but nothing we can't handle. We're looking for a volume, so question mark. Milliliters of acetic acid is equal to 5.6 grams of it's equal to 5.6 grams of sodium hydroxide. First thing I'm going to do is I'm going to convert from grams to moles. Moles are our chemistry unit that we want to work with whenever possible. Now I can use my balanced chemical equation to go from moles of sodium hydroxide to moles sulfuric acid. Finally then, I know the strength of my acid, 6 moles per milliliter. So I cross out the values and I end with a 12 milliliter volume of acid would be required. All right, practice makes perfect. So here is homework 16.3. It says it's assigned Thursday, but it'll be assigned today, Wednesday, and it'll be due Thursday. So at least they got the due date up here, Thursday, but it's assigned today.